Welcome to the second lecture. So in the first lecture we have seen three different characterizations of the random variable and the random vector. So the first characterization was the probability distribution. So I had Pz of z, which was defined as probability of z in being in z. Okay? And the second characterization was CDF, and it was f of z of psi is equal to the probability of z is smaller than or equal to psi. And the third characterization was the most common, which is the density function. So I have Pz of z is equal to d over dz times the cumulative distribution function. Okay, so I have z here. So in the last lecture I have actually shown you, I have told you that it is getting weaker and weaker as I go towards below here. Okay, so but we are going to assume in this course that the weakest form of characterization, which is the density function, exists. Therefore, all of them are going to be equivalent. So in the last lecture, in the first lecture, I have written Pz in terms of the distribution function and Fz in terms of the distribution function here. So here I can actually do the reverse if I assume that the density function exists. So I can actually write all of the upper ones in terms of the last one here. How can I do that? So I have Pz of capital Z is an integral with Pz of z dz, and I need to integrate over this subset of Rn. Okay, so this is a multiple. There are multiple integrals here because Z has many variables in it. It's a vector, and that means that I have here, I need to integrate the density function to calculate over this subset to calculate the probability of Z being in that subset. So similarly, the cumulative distribution function can be written in terms of the density function. So that means that that is nothing but Z psi. There are again multiple integrals here. This is going to come from -infinity to the variable psi, and I have Pz of z dz. Okay? So the cumulative distribution function can be written in terms of PDF, just like this. So now we're going to go into the study of probability of multiple variables. So I'm going to define two vectors, Z1 and Z2 are random vectors. Let us say that they have different dimensions. Z1 is a random vector, which is a function from the set of outcomes into Rn1, and Z2, let us say that it's a function from omega to Rn2. So Z1 is a random vector of size n1, and Z2 is a random vector of size n2. So now I can actually again define the characteristics for these double random vectors. In that case, these quantities are called joint distributions, joint cumulative distribution functions, and joint probability density functions. Okay, so I can define Pz1, Z2, and this is going to be a joint distribution function, and that is going to be the probability of Z1 being in Z1 and at the same time Z2 being in this subset capital Z2. Okay, so here where capital Z1 is a subset of Rn1 and capital Z2 is a subset of Rn2, the spaces of these, or the codomains of the random vectors here. Okay, and this is called joint distribution function, joint distribution of Z1 and Z2. If you have if you have more random vectors, then you can increase the order of this joint distribution. So now let us define joint CDF. So I have Z1, Z2. In this case, I have two vector variables, psi1 and psi2. And this is definition. Probability of Z1 is smaller than or equal to psi1, and Z2 is smaller than or equal to psi2. So here, when I put a comma here, I am actually taking the intersection of both of these events. This is an event, this is an event, and I want to find the probability of their intersection. So in this case, you have to think these as events, and I want to find the probability of their intersections, meaning the probability of both of them happening at the same time. So here I have the same thing. These are again element-wise inequalities. And I want both of these conditions to happen, both of these events to happen at the same time, and I need its probability as the joint CDF. This is joint CDF of Z1 and Z2. And finally, we have the joint PDF, which is the most common. So P of Z1, Z2 and Z1, Z2 is equal to, I have to take the derivative here of the cumulative distribution function. So this is Z1, Z2, Z1, Z2. Okay? So this is the joint PDF. PDF of Z1 and Z2. Okay? So of course, when you know the joint PDF or joint cumulative distribution function or the joint distribution function, then this is much more powerful than knowing the individual marginal distributions. Okay? So this is so I can have P of Z1, Z1, and P of Z2, Z2. So this is a marginal distribution function of Z1. This is the marginal distribution function of Z2. Knowing the joint distribution function of Z1 and Z2 is much stronger than knowing these individual distribution functions. That means that when I know the joint distribution, I can obtain the marginal distributions given like this. From this one, I can obtain this in these individual ones. How can I do that? The same thing is correct for the joint CDF and joint PDF. Let us now try to obtain those marginal quantities from the joint distributions and joint characterizations. So I can actually write right here the marginal quantities. Or this is sometimes called marginalization. So suppose that I know the joint distribution of the random vectors Z1 and Z2, and from those I need to obtain the marginal distribution of which one in my notes I'm obtaining the marginal distribution of Z1. Okay? So from this one, how can I obtain this marginal distribution, the first distribution function? So I need to write here, I will do it only for the first random vector, and the second one can be obtained similarly. So I have P of Z1 given the subset Z1 is equal to, I need to reduce this double or joint distribution function into the marginal. How can I do that? I can do that by converting this second event related to Z2 into a sure event. Okay? So a sure event is an event which has to happen with probability 1. Okay? So here I can actually reduce this joint probability into a marginal probability by making sure that the second event is a sure event, which is an event which has probability 1 of happening. Okay? So how can I choose capital Z2 such that the event small z2 inside capital Z2 has probability 1. Okay? I can do that actually by choosing Z2, the overall space of the random vector, which is Rn2. Okay? So I can actually make the marginalization of this joint distribution as follows: Z1, Z2. I keep Z1 as it is, and instead of Z2, I substitute Rn2. In that case, this event happens a sure event, so I can actually remove this event, this event from this probability calculation, and that would give me the marginal distribution function like this. So here, let us do that for the CDF. So I have f of Z1 psi 1, the marginal CDF of the random vector Z1 can be written in terms of the joint CDF of Z1 and Z2. I put psi 1 here, I keep psi 1 here, but instead of psi 2, I am going to write here a vector which would make this second event a sure event. Okay? An event which happens with probability 1. Okay? So which value of psi 2 makes the event Z2 smaller than or equal to psi 2 a sure event? Obviously, for this event to have probability 1, I can actually substitute infinities here instead of psi 2. Then Z2 smaller than or equal to infinities would have probability 1. So that would be a sure event here. So here, I substitute here infinity. But this is an element-wise inequality, and I want all of the elements so psi 2 is a vector with as many elements as Z2 here. And Z2 has n2 elements, therefore psi 2 has n2 elements. And I want to make all of its elements infinity. Okay? So that means that I need to put here a vector of ones with size n2. Okay? So this is 1, 1. And they're all ones. There are n2 ones here, okay? And I multiplied with infinity, making all of the elements infinity here. So this is the marginalization in terms of the cumulative distribution functions. So you substitute the second argument infinities. If you substitute the first argument infinities, then you would marginalize with respect to the, you would marginalize out the first variable, and you would get f of Z2 psi 2. And probably the most common is the marginalization of the joint PDF. So we know that I can actually obtain the marginal PDF of the variable Z1 by integrating out Z2 here. Okay? So this is P Z1 Z2. I would have here Z1 Z2. The marginalization happens by integrating with respect to Z2 over the whole space of Z2. Okay? So this is the marginalization for the second variable. All right? So now we have remembered how to apply marginalization with respect to different characterizations. Now I'm going to look at other joint concepts. So now let us look at cross-covariance matrix. So in this case, I will call the joint covariance matrix of the random vectors Z1 and Z2 like this, sigma Z1, Z2. This is defined as expected value Z1 minus Z1 bar, these are the expected values of Z1 and Z2. These barred quantities are the expected values minus Z2 bar transpose. Okay, so this is called the joint cross-covariance matrix of the random vectors Z1 and Z2. And here, Z1 bar is expected value of Z1, and Z2 bar is expected value of Z2. Okay? And I can actually write the cross-covariance in the following form. I have double integrals, Z1 minus Z1 bar, Z2 minus Z2 bar, transpose, and I need to write here, obviously, the joint distribution of Z1 and Z2. And I need to integrate over the whole space. The inner integral is with respect to Z1, so this is Rn1, and this is R over Rn2. All right? So I have the cross-covariance matrix, and based on the cross-covariance, I can actually define the concept of uncorrelatedness. So let us write definition. Two random vectors, Z1 and Z2, are called uncorrelated if and only if, so this is the definition, sigma Z1 Z2 is equal to the zero matrix. So if the cross-covariance matrix is equal to the zero matrix, by the way, what is the size of this matrix? So the Z1 has n1 elements, Z2 has n2 elements, so the size of this matrix is n1 by n2. Okay? So if this cross-covariance matrix is, if it is zero, then we call these random vectors uncorrelated random vectors. Okay? So in order to actually interpret this result, I need to write the cross-covariance matrix in another form. So in order to be able to do that, I will actually expand this outer product, just as I did in the covariance calculation. Okay? So I have this outer product, it's a rank 1 matrix if both of the vectors are non-zero. Then that is equal to, so I have Z1, Z2, transpose of course, minus Z1 bar Z2 transpose, minus Z1 Z2 bar transpose, minus Z1 bar Z2 bar transpose. And then I'm going to take the expectation of both sides. The left-hand side of the expectation of the left-hand side is going to give me sigma Z1 Z2. This is the cross-covariance matrix. And expectation of the first term, it is expectation Z1, Z2 transpose, minus, here Z1 bar is a deterministic variable, okay? So it can get out of the expectation directly, and here I need to take the expected value of Z2, which is Z2 bar, okay? So this is Z1 bar minus Z2 bar transpose, minus, here I have the same thing, Z2 bar is deterministic, gets out of the expectation, I take the expectation of Z1 only. So I have Z1 bar, Z2 bar transpose minus Z1 bar, Z2 bar transpose. So here there is this mistake, this has to be a plus sign. So, and these terms are cancelling, as you see. So the cross-covariance matrix is nothing but sigma Z1, Z2 is the expectation of Z1 times Z2 transpose minus Z1 bar, Z2 bar transpose. Okay? And these are nothing but the individual expectations of Z1 and Z2. So this is equal to expected value Z1, Z2 transpose minus expected value of Z1 an expected value of Z2 transpose. Okay? So we see that there is an expectation of the multiplications, and then the multiplications of expectations are subtracted from that. So I know that two random vectors are called uncorrelated if this cross covariance is 0. And here, by using this definition of the cross covariance, I can say that the random vectors are uncorrelated if and only if the expected value of this multiplication is equal to the multiplication of the expectations. Okay? So I can write here Z1 and Z2 are uncorrelated if and only if expected value Z1, Z2 transpose is equal to expected value of Z1 times expected value of Z2 transpose. Okay? So an equivalent definition of uncorrelatedness is that the expectation of the multiplications is equal to the multiplications of the expectations of the random vectors. So here I can, for uncorrelated random vectors, I can distribute the expectation over the multiplication of elements. So now this was the definition of uncorrelatedness. There is so it is the relationship between these random vectors. So uncorrelatedness is a form of relationship between the random vectors. If the random vectors are uncorrelated, then I know that there is little relationship between these random vectors. And actually, there is an even weaker type of relationship than the uncorrelatedness, and that is the independence. Okay? So now let us try to see that. Definition. The random vectors Z1 and Z2 are called independent uncorrelatedness means weak relationship. Independent means absolutely no relationship. Okay? So here are called independent if and only if any one of the following is true. Is true. So if two random vectors are independent, then their joint distribution function given like this can be factorized into its marginal distribution functions. These are small ones. So this is PZ1, capital Z1, PZ2, capital Z2. Okay? Distribution functions can be factorized into multiplication of the marginal distributions. Similarly, the CDFs are factorized. Any one of them would imply independence. Z1, Z2, psi1, psi2 is equal to the multiplication again. Factorized into marginal CDFs. Okay? And the third description is about the density functions. PZ1, Z2, Z1, Z2 is equal to PZ1, Z1, PZ2, Z2. Okay? Any one of them is equivalent to random variables being independent. Okay? So independent means absolutely no relationship between the random vectors. So correlation is uncorrelatedness is a weaker form of relation. There might still be some relationship between the variables, but it's a weak relationship. So therefore independence is a stronger condition. It requires stronger properties. And therefore I can actually say that independence actually implies uncorrelatedness. Okay? But the other implication, uncorrelatedness in general, does not imply independence. Okay? So here, just in order to see that, let us assume that Z1 and Z2, suppose Z1 and Z2 are independent. Okay? Then I'm going to try to calculate expected value Z1, Z2 transpose based on the independence assumption. Okay? So this expectation is, so this is a this is not cross correlation, cross covariance matrix, sorry. So this is I have double integrals Z1, Z2 transpose, and I need to integrate it by multiplying with the joint density. Okay? Z1, Z2, dZ1, dZ2. Okay? That is the definition of the expectation of Z1, Z2 transpose. So now I know that Z1 and Z2 are independent, therefore this density, this joint density can be factorized into marginal densities. So that means that I have double integrals Z1, Z2 transpose and PZ1, Z1, PZ2, Z2, dZ1 and dZ2. Okay? So now you see that the Z1 related terms and the Z2 related terms can be decoupled here. Okay? So this double integral can be written as the multiplication of two integrals, Z1, Z1, dZ1, times I have Z2 transpose PZ2, Z2, dZ2. Okay? A double integral, because the argument of the integral can be factorized, it can be separable, can be separated into two factors which are dependent on only Z1 and only Z2, then this double integral can be written as the multiplication of two single integrals. Okay? And this is nothing but expected value of Z1 and expected value of Z2 transpose. So we started with Z1 and Z2 being independent, and we showed that expected value of Z1, Z2 transpose is equal to the multiplication of the expectations of Z1 and Z2. That means that these random variables Z1 and Z2 are uncorrelated. So what does this mean? This means that in general, independence implies uncorrelatedness. So if two random vectors are independent, then they are surely uncorrelated. But what about the reverse implication? If two random variables are uncorrelated, are they independent? In general, the reverse implication is not correct. Okay? So there can be two uncorrelated random variables which are not independent. Okay? But actually there is a very, very specific case in which the other, so in general the reverse implication is not correct, but there is a very, very specific case in which the reverse implication would actually hold. And if you know that specific case now, then that means that your probability background is quite nice. Okay? If you don't know when the reverse implication would hold now, then that means that you will need to study probability theory still for this course. So here, now we're going to go into the concept of conditioning. When random variables are not independent, then knowing something about one of the random variables would give us information about the other random variable. Okay? When two random variables are not independent, which means they have a relationship between each other somehow, then knowing something about one of the random variables would give us information about the other. And that brings us to the concept of conditioning. Okay? So knowing Z1 or knowing something about Z1 would bring us information about Z2 and vice versa. Okay? So here, let us see the concept of conditioning. So we are again going to define some characterization of conditioned random variables. Okay? So I will define a conditional distribution of the random vector Z1 given Z2. Okay? So this is going to be capital Z1 given capital Z2, and that is going to be the probability of Z1 is inside capital Z1 given that Z2 is inside capital Z2. Okay? So here, if these two random variables are not independent, then knowing that Z2 is inside a subset would give us information about the probability of about the event of Z1 being inside capital Z1. Okay? So knowing something about the second random vector would give us information about the first random vector. So without this conditioning, this probability only would be different with the conditioning. Okay? So knowing one of the variables would give us information about the other variable. So this is a conditional distribution function, and actually I can define what that conditional distribution function by using the probability rules. So this is equal to probability of Z1 inside capital Z1 and Z2 inside capital Z2 divided by probability of Z2 inside capital Z2. Okay? So this is coming from the conditioning rules in probability theory. Okay? This conditioning would be the joint probability divided by the marginal probability given in the conditions. Okay? And what is this joint probability? Maybe I need to erase this part as well. This joint probability is nothing but the joint distribution function, and this is the marginal distribution function. So this is equal to, I would have here P Z1, Z2, and I would have here the subset Z1 and Z2 divided by PZ2 and subset Z2. Okay? So the conditional distribution function is given by the joint distribution function divided by the marginal distribution function in of the random vector in the condition. Okay? And actually, I can write this as follows. So I have P Z1, Z2, Z1, Z2, divided by, this is a marginal distribution, but I can obtain this marginal distribution function from the joint distribution function as follows. So I can put here Rn1 and Z2. Okay? Because this marginal distribution is nothing but the joint distribution when I substitute the capital Z1 as Rn1. Okay? So I will not write the CDF version of this rule. I will directly go into the PDF version. So the PDF version, so the density version, which is going to be more useful for us, and it is what it is used usually. So this is the density version. Okay? So I have P Z1 given Z2, Z1 given Z2 is equal to, in general, it is the joint distribution, joint PDF, divided by the PDF of the variable in the condition. Okay? So these are all small p's. So the conditional distribution is nothing but the joint distribution of the random vectors divided by the distribution of the variable in the conditioning. Okay? And I know that this marginal density here is nothing but the integral of the joint distribution over Z1. Okay? So I can actually write this formula as follows. P of Z1, Z2 divided by the integral of the joint distribution with respect to Z1. Okay? P of Z1, Z2 dZ1. And this integral is over the whole space of the random vector Rn1, random vector Z1. Okay? So you see that here, this is a form, so this distribution is a distribution for Z1, given some quantities. So as a result, the integral of this distribution with respect to Z1 should be 1. So this number in the denominator is nothing but a normalization constant for the distribution that is given here. So this is nothing but a normalization constant with respect to Z1. So that the integral of this quantity is just, with respect to Z1, is just equal to 1. Okay? So you might remember that in the probability course, the conditioning concept is one of the most difficult concepts in probability theory. But in this course, we will need to find the conditional distributions of the, let me write this. In this course, when we see the linear systems, we will need to find the conditional distribution of the state vector xn given all of the previous measurements. Okay? This conditional distribution is actually going to be a Gaussian vector. Okay? It's going to be a Gaussian distribution. And it is going to be a Gaussian distribution with respect to xn, and it's going to have a mean, xn given n, and it's going to have a covariance, n given n. Okay? And we are going to see that if your linear system has also Gaussian noises, which means that you have a linear Gaussian system, then we will be able to find some recursions for this mean and for this covariance. And those recursions are called in the literature as the Kalman filter. So it's the most famous observer for a stochastic linear Gaussian system, where we might see that it is going to be the optimal observer in the minimum mean error, what was it? Minimum mean error, squared error, MMSE sense, okay? So here, therefore, we will definitely need the concept of conditioning in this course. So understanding, a good understanding of conditioning is necessary for this course. So let us look at an example. So here, I will just draw the joint PDF of two random variables. So I have Z1, Z2. These are scalar random variables. So I have Z1, Z2 here. And the joint PDF is going to be uniform on a triangle. Okay? So I have this variable as Z1 and this variable as Z2, and this point is 1 and this point is 1, and I will draw here a triangular region. All right, so it will be looking like this. On this triangle, so the PDF is uniform, which means that on this triangle it is all equal. It has all equal values. Sorry for my drawing skills here. So on this triangle we have equal values, and it is 0 everywhere else. All right. So if I try to draw this on a two-dimensional plane, so it is this triangle that I'm talking about. Inside this triangle, the joint PDF has equal value everywhere, and it is 0 everywhere else. All right? So now the task is find probability. So it is PDF Z1 given Z2, Z1 given Z2 is equal to 1 over 3. Okay? Suppose that somebody gave us the value of Z2, okay, which is equal to 1 over 3, and I need to find this conditional distribution. Okay? Conditional PDF, I mean. Sometimes when I say PDF, sometimes I say probability distribution function, but I don't really mean this one. Okay, this one takes subsets inside. I'm meaning PDF in almost all cases. So now you might actually remember how to find such conditional PDFs. So here I will use this formula here. Okay. So P of I will Z1 given Z2 and Z1 given 1 over 3 is equal to, in the joint PDF, I will substitute the value of 1 over 3. Okay? And then I will divide this result with the integral, and I will substitute Z2 equals to 1 over 3 still. So I have P of Z1, Z2, Z1, 1 over 3, dZ1. Okay? So now you see that I fixed the value of Z2 at 1/3, and then I look the joint distribution as a function of Z1, okay? And then I would normalize this joint distribution as a function of Z1 with respect to Z1, and I divide by this number, so that the integral of this conditional distribution with respect to Z1 would be 1. This is a proper density function for the random variable Z1, okay? So now, the first thing that I'm going to do is to find what this constant value of the PDF is. The joint PDF has some value constant over this triangle. What should be that constant value? I know that the integral of PZ1, Z2, Z1, Z2, dz1, dz2 should be 1. Okay? I know that any density function, if integrated with respect to all of its arguments, should integrate to 1. Okay? So as a result, when I take the integral of this joint PDF over this triangle, the integral should be 1. Okay? But this integral is going to be the area of the base, which is area of this triangle, times the height. Okay? So if I call this number as h, then this integral would be the integral of the base, integral of the triangle there, 1/2 times the height should be equal to 1. Okay? That means that h, the height, is going to be 2. Okay? So here, this density function, this joint PDF, is constant at the value 2. Inside this triangle, and it is 0 everywhere else. And then I'm going to look at this function. What happens when I fix one of the arguments of this density function at Z2 equals to 1/3. Okay? So I'm going to look at this cross section. Okay? So this is the value of 1/3 for Z2, and then I will be looking at this cross section of this density function here. Okay? I see that it is constant, which is equal to 2 over this non-zero region, and then it becomes 0. What is this value, Z1 value, at which it again becomes equal to 0? So when Z2 is equal to 1/3, so I put here 1/3, what is this value? What is the Z1 value? If you look at the equation of this line, it is nothing but Z2 equals to 1 minus Z1. Okay? So when Z2 is equal to 1/3, then Z1 is equal to 2/3. Okay? So here, this intersection here is 2/3. Okay? And then I'm going to look at this cross section, because I'm actually trying to obtain this function as a function of Z1. So now I would like to draw that function with respect to Z1. P of Z1, Z2, Z1, and Z2 is fixed at the value 1/3. Okay? So you see that at Z1 is equal to 0, it is going to be equal to 2. And then when the Z2 is always fixed, when I increase Z1 like this, it's going to remain constant until we hit Z1 is equal to 2/3. Okay? So I have here 2/3, and the function is equal to 2 in this interval, and it is 0 everywhere else. Okay? So this is the joint distribution, the cross-section of the joint distribution when I fix the Z2 variable. When I know Z2, this would be the joint distribution with respect to Z1, that cross-section of the joint distribution. But this is still not a density function for Z1, okay? The thing that I want to calculate is a density function for Z1. So the integral of that quantity should be equal to 1 when I try to integrate it with respect to Z1. But the integral of this function is nothing but 2 times 2 over 3, which is 4 over 3. Okay? Therefore, this is not a density function. So in order to be able to convert it into this conditional density function, I need to divide it by this integral. What is this integral? Integral of this function with respect to Z1. But I have just calculated that integral. What is that? So I have P of Z1, Z2, Z1, 1 over 3 dZ1 is the integral of this function is 4 over 3. Okay? So what I'm going to do is that I'm going to divide this function by 4 over 3. Okay? Then the 0 parts would remain as 0 and divide 2 by 4 over 3. Okay? So now this is going to be, I have PZ1. This is going to be the conditional distribution. Z1 given 1 over 3. And now this has to be a density function. Divide this distribution, divide this function with its integral with respect to Z1, which is 4 over 3. Then 2 over 4 over 3, it's going to give me 3 over 2. So I have 3 over 2, and it's 0 in the interval 2 over 3, and 0 here, and 0 everywhere else. Now the integral of this function, which is the conditional density, would be equal to 1. So 3 over 2 times 2 over 3 is equal to 1. So you see that this is a proper density function for Z1. This is a density function of Z1 when Z2 is given to us. Okay? So what would happen if I have chosen other Z2 values? Okay? For example, what would happen if Z2 was equal to 0? In that case, I would look at this cross-section. So the support of this distribution would be enlarged when Z2 is smaller than 1 over 3. Okay? If I take Z2 values larger than 1 over 3, the support of the uniform distribution would get smaller and smaller. Okay? So you see that by changing the Z2 value, the conditional distribution changes. So the support of this distribution, the conditional distribution of Z1 would change. So now we are ready to see what would be the effect of independence on conditional distribution. Let us look at a theorem. Z1 and Z2 are independent if and only if the conditional distribution is equal to the marginal distribution of Z1. Okay. So you see here something interesting, that if Z1 and Z2 are independent random vectors, sorry, this is independent random vectors, then the conditional distribution of Z1 given Z2 would be equal to the marginal distribution of Z1. Okay? So this Z2, knowing the value of Z2 would bring no information at all into our Z1 knowledge. Okay? So when Z2 is given, our knowledge about Z1 is equal to our initial knowledge about Z1, our marginal knowledge about Z1. So knowing Z2 does not bring any new thing to Z1. Okay? So let us now look at the proof of this theorem. Of course, this is an if and only if statement. That means that it's a double-sided implication. So I will first look at the implication of this side. Implication this side. So I will assume Z1 and Z2 are independent. So Z1 and Z2 are independent, let us say. This means that P of Z1, Z2, Z1, Z2. So I will here not keep the subscripts. I will remove the subscripts, okay? Because I'm always repeating them here with no purpose. So if Z1 and Z2 are independent, then PZ1, Z2, the joint distribution is PZ1 times PZ2. Okay? And here I'm going to try to prove that this conditional distribution is the marginal distribution. Okay? So PZ1 given Z2, it is by definition the joint distribution divided by PZ2. Okay? Since the joint distribution is this factorization due to independence, I have PZ2 given PZ2. Here, these PZ2s are cancelled, and I would have just PZ1. Okay? So in the case of independence, the conditional distribution reduces to the marginal distribution. So I can remove this variable from the conditioning if there is independence. So do you think in this case, in this example case, I can remove this conditioning? So do you think in this case I can remove this conditioning? So do you think PZ1, Z2, Z1 given Z2 is equal to this marginal distribution? So you see that when you have this equality, this conditional distribution should not change with respect to the value of Z2. Okay? Because the right-hand side is not dependent on Z2 at all. Therefore, the left-hand side should not depend on Z2 either. Okay? So when I change Z2, this distribution should not change if I have independence. So here, when I change this value of Z2, 1 over 3, we see that this conditional distribution would change. Its support would change. As a result, I can say that here Z1 and Z2 are definitely not independent. Okay? They are dependent random variables, because this conditional distribution would depend on, if I change 1 over 3 to any other number, this conditional distribution would change. Its support and its values would change. As a result, in this joint distribution case, Z1 and Z2 are actually dependent random variables. So this was the first part of the proof. So I have only proven the implication towards the right. So I can look at the other implication. It is really quite easy. It's not difficult. So now let us look at the reverse implication. So now I will assume that this equality holds. Okay? Suppose P of Z1 given Z2 is equal to P of Z1. Okay? Suppose this equality holds, then I know that what this is PZ1 Z2 given PZ2. This has to be equal to PZ1. Okay? And taking PZ2 to the other side would give me PZ1, Z2 is equal to PZ1 times PZ2. This means that Z1 and Z2 are independent. Okay? So now as we see that, so this is equivalent, this condition is equivalent to independence. If the random variables are independent, this condition holds. If this condition holds, then the random variables are independent. Okay? So we can check independence equivalently by using this condition. Let us solve an example. Consider the following joint distributions. For Z1, Z2 inside R. Comment on the independence of Z1 and Z2 for both cases. Okay? So the examples would be similar. So I would have Z1 and Z2 similar to the earlier example. So in the first case, I would have a square, and on this square, the joint distribution would be uniform. Okay? So here this point is 1, minus 1, 1, and minus 1. And in the other case, I would have the joint distribution also uniform, but in this case, on a diamond shape like this. Okay? Minus 1, 1, 1, minus 1. So the variables are here Z1, Z2, and Z1, Z2. And in this case, I have a uniform random variable in both cases. Okay? So one of the cases is going to be independent case, and in the other case, we would have dependence. Okay? So in order to be able to decide on independence, I would be looking cross sections of these distributions. Okay? So if I look at the Z1 value, if I fix the Z1 value, then I would look the non-zero Z1 probability region. So Z1 would have 0 probability outside this range. So I would look at only the range of Z1 values between this interval. Okay? And then I would look at the cross sections by fixing Z1. Okay? So this is Z1 is equal to, for example, 2 over 3. This is Z1 is equal to minus 2 over 3, etc. So these cross sections, I would know that for these cross sections, if I look at those functions with respect to Z2, then they would be uniform distributions. And furthermore, if I change Z2 value, those uniform distributions would not change at all. Okay? So I'm looking at only the range of Z1 values which has non-zero probability. So inside this range, when I change Z1 and when I look at the cross sections of this function here, I would see some uniform distributions between minus 1 and 1, and those uniform distributions would not change if I change the Z1 value. On the other hand, here, when I look at these cross sections, the similar cross sections here, I would see that when I change the Z1 value, those uniform distributions would change their support. Okay? Therefore, the conditional distribution Z2 given Z1 would change depending on the value of Z1. Here, on the other hand, it is independent of the Z1 value. Okay? That means that in this case I have independent Z1 and Z2, and in this case Z1 and Z2 are dependent. Okay? So now we have seen the concept of conditioning. Now we can look at conditional expectations. Conditional expectations. So in this case, I'm going to look at the expectations of this form. I have a function of Z1 and Z2, a joint function of Z1 and Z2. I will look at its expectation given the variable Z2. Okay? So this is called a conditional expectation. Okay? Now I'm going to write its definition. So this is nothing but integral. So I have the function q of Z1, Z2, and I have p of Z1 given Z2, Z1 given Z2. And this is integral over Z1. Okay? And this is over the whole. If I don't write the integration limits, that means that it is the whole space of the random variable Z1. So here, what this expectation is doing is that it is removing, so this is an expectation with respect to Z1, given the random variable Z2, okay? So this expectation is actually removing the random parts of this function due to Z1. The integration is with respect to Z1, and I would have here, in the given condition, I would have Z2, okay? So here, when I look at this expectation, it is going to, in general, it's going to depend on Z2, okay? So because this distribution, in general, when we don't have independence, because this distribution depends on the value of Z2, the result of this expectation would still depend on the value of Z2, okay? So this expectation only removes the random parts of this function with respect to Z1. And the random parts with respect to Z2 would still remain after the expectation. Okay? What does that mean? Let us write. Expected value Q of Z1, Z2 given Z2 is still a function of Z2, and hence it is still a random variable or a random vector, if you wish, okay? Depending on the structure of the function Q. All right? So here, this is still a function of Z2. That means that this is still a random quantity. If I don't specify Z2, then it is still random. So now we have some specific cases. So for example, Q of Z1, Z2 can be just equal to Z1. Okay? In that case, this is going to give me the conditional expectation of Z1 given Z2. Okay? And I can actually call this as z bar 1 given 2. Okay? And this is going to be, if I write it as an integral, again, it's going to be z1, and I have p of z1 given z2 dz1. This is the conditional expectation or conditional mean of z1 given z2. And I can also have the conditional covariance. So z1 given 2 is still a function of z2. This conditional mean is still a function of z2. If I change z2, it would change, because this density would change in that case. So if I define q of z1, z2 in the following form, z1 minus z bar 1 given 2, z1 minus z bar 1 given 2. Transpose. In this case, z1 is a function of z1, and this z1 given 2 is a function of z2, so I have a function of z1 and z2 at the same time here. So if I take the expected value of this thing, then I would obtain the conditional covariance of z1 with respect given the value of z2. So I have sigma 1 given 2 is equal to expected value of that quantity. So I have z1 minus z1 given 2 bar, z1 minus z1 given 2 bar, transpose given z2. Okay? So I would have this expectation, and this is called the conditional covariance. So if I write this, if I write what z1 given 2, z bar 1 given 2 here, this would look like this. z1 minus expected value z1 given z2, and z1 minus expected value z1 given z2 transpose given z2. Okay? And this is nothing but the conditional covariance. Covariance of z1 given z2. And this is conditional mean of z1 given z2. Here, in these examples, if you look at the conditional mean of z2 given z1, then what can you say about that conditional mean? So the conditional distributions here would be uniform distributions, symmetric around 0. So the conditional mean of z2 given z1 would be equal to 0. It would be independent of the value of z1. Okay? What about the conditional variance? The uniform distribution would be the same. It wouldn't depend on the z1 value. Okay? So the conditional variance would also be the same. But this is actually the result of the independence of these z1 and z2 for this case. Okay? So when the random variables are independent, then you can remove this z2 from the conditioning. Okay? So if the random variables are independent, then the conditional covariance sigma 1 given 2 would be the marginal covariance sigma 1 of the random variables z1. Similar equation holds for the mean as well. So if there is independence of z1 and z2, expected value z1 given z2 would be just expected value z1. Okay? What about the second variable? second case here. So in this case, when Z1 changes, the uniform distribution would change, but it would be still symmetric around 0. So the conditional mean of Z2 given Z1 would be equal to 0, independent of the Z1 value. What about the conditional variance? In that case, when I change the Z1, since the uniform distribution is expanding its support, so the conditional variance would get larger and larger. It would be a maximum here, and it would get smaller and smaller. Okay? So we have actually seen the conditional mean and conditional variance, and the final thing here in the conditioning that we are going to see is going to be the iterated expectations. So this is going to be a theorem, and this theorem is called law of total expectation. Okay? And it says something like this: expected value of Z1 given Z2, this expectation is equal to expected value of Z1. So this is for a single random vector Z1, and it is also true for its function. Expected value of Q of Z1 given Z2, and I would have this second expectation. It is equal to expected value of Q of Z1. So it is true for an arbitrary function of Z1 as well. Now I will look at these expectations here. So this expectation, the inner expectation, is expectation with respect to Z1 given Z2. So Z2 is specified here, and I'm taking expectation with respect to Z1. Okay? What about this second expectation? I know that this conditional expectation is still a function of Z2. So when I take the inner expectation here, all randomness related to Z1 disappears, but the randomness related to Z2 would remain. So the inner expectation would be a function of Z2. As a result, the second expectation is only with respect to Z2. Okay? So the outer expectation is with respect to Z2, inner expectation is with respect to Z1 given Z2. What about this expectation on the right-hand side? This function is only a function of Z1, and that means that this expectation is with respect to Z1. Okay? So the proof of this thing is not really difficult. Let us quickly go over it. So I will first write what the inner expectation is. Expectation Q of Z1 given Z2 is equal to integral Q of Z1 P of Z1 given Z2 dZ1. Okay? This is a conditional expectation. Z2 is given to us, and therefore I need to take expectation with respect to the density Z1 given Z2, and I need to integrate with respect to Z1. And what about the outer expectation? The outer expectation is with respect to Z2 only. Expected value Q of Z1 given Z2. This is a function of Z2 only. As a result, this expectation is with respect to the marginal distribution of Z2. So now I can actually substitute the first formula here inside the second formula. Okay? Integral. Instead of this one, I will write this integral. Q of Z1, P of Z1 given Z2, P of Z2, dZ2, dZ1. Okay? So now what is the multiplication of these two distributions? I know that this conditional distribution is nothing but PZ1, Z2, joint distribution divided by PZ2. Okay? And PZ2s are cancelled. So this is nothing but PZ1, Z2. Okay? So that is equal to double integral Q of Z1, PZ1, Z2, dZ2, dZ1. Okay? And now I see that I can actually take the integral with respect to Z1 here, because the only argument, the only function which is dependent on Z2 here is this one. Okay? So that is equal to Q of Z1 integral PZ1 Z2 dZ2. This is the inner integral, and I have dZ1. Okay? And what is this integral? So I'm integrating the joint distribution with respect to Z2 over the whole space. So this would cancel Z2 variable. This would give me the marginal distribution of Z1. Okay? And then this is going to be Q of Z1, P of Z1, dZ1. But this is nothing but expected value of Q of Z1. Okay. So we have this number is equal to this one. Okay? So it is equal to this one as well. So this is called the law of total expectation, or sometimes it's called law of iterated expectations. So when I look at an expectation here like this, I can add some conditioning, and I can then remove it with another expectation. This is going to be one of the tools that we will need to use. So we have now seen the concept of conditioning. In the next lecture, the first thing is going to be to consider two jointly Gaussian random variables. And then we are going to look at scalar random variables. And then we are going to be looking at their conditional distributions. All right? We will see that when you have jointly distributed Gaussian variables, the conditional distributions would also turn out to be Gaussians, and we would really have nice results for their conditional expectation and conditional mean and conditional covariance, actually. And then we're going to see a very interesting property about Gaussian distributions by considering those conditional mean and covariance. But that is going to be all for this lecture. Thank you very much for watching. Bye-bye.